Hello everyone, my name is Badri Adhikari and welcome to the Advanced Data Structures and Algorithms course. We will start with the first chapter, um, Analyzing Algorithms, where we discuss growth of functions and divide and conquer. What I would like to do is discuss some problems that are solved by algorithms, basically bring up some real world examples of problems where algorithms are needed, and then sort of motivate you to understand that algorithms have values in today's world, and make you feel motivated to learn the algorithms in the course, implement the algorithms in this course. So what I'd like to do is come up with, I can start by discussing a broad range of problems that algorithms can solve, and also discuss some specific problems that algorithms can be used to solve. So algorithms can be used to solve biological problems. For example, our human DNA contains 3 billion base pairs, basically 3 million characters, and storing one single person's DNA requires at least 1 GB of storage. So this is just for one person. Imagine how much space you would need to store, say, the DNA of 1,000 people. That would automatically be 1,000 gigabytes, right? And if we wanted to do something known as pairwise DNA comparison, what that means is we would like to compare the DNA of one person with every other person, and compare each other's DNA with each other. Then that is a lot of computation. During my PhD, I myself worked on a project called Chromosome 3D, where we took the data from lab experiments and built three-dimensional structures of human chromosomes. Let me take you to that page, the web server that actually can build 3D models of human chromosomes. So here's the web server that we developed. The tool is known as Chromosome 3D, and here's the 3D models of human chromosomes visualized using a tool known as UCSF Chimera. Now, even though these models look very tiny, it takes a lot of computation to actually build these 3D models of chromosomes. Another set of problems exist in the way the internet works. Internet enables people to access a large amount of data quickly and within seconds, right? How can websites manage and manipulate such large volumes of data? Of course, it's all through the use of algorithms. Once again, how do we find good routes on which the data will travel across the internet, across servers and routers? That's again handled by algorithms. Another example would be analyzing data for winning an election. Say, for example, a political candidate wants to determine where to spend the money for advertising in order to maximize the chances of winning an election. So there are many parameters that come into play. For example, population of the various states, type of area, buildings, roads, tax, farm subsidies, and all these issues come into play. So how should a political candidate sort of optimize all of these information that's supplied by the campaign in order to maximize the chances of winning election? Once again, we'll need algorithms to solve problems like these. Let's look at some specific problems. One very common problem that's solved very well by algorithms is the shortest path between two cities. Say, for example, from the University of Missouri, St. Louis, UMSL, we want to go to Fontbonne University. How do we find the shortest path between cities or between places, right? Obviously, algorithms. And then what would we do if we did not have algorithm for finding shortest path? Of course, we would have to spend a lot of time relying on heuristics, intuitions, and then wasting a lot of time every time we have to go on memorizing them, keeping the track of the shortest path that people have found and maintaining a book of shortest paths, right? Probably shortest path book and so on. But fortunately, having algorithms, we can calculate these at runtime mostly. Another common problem is a problem known as the longest subsequence problem. Imagine a sequence of characters. Let's say the sequence is represented by X, where the characters are X1, X2, da 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 da, all the way up to Xn. And then let's say you have another sequence Y, which has characters Y1, Y2, all the way through Ym. And let's say these characters are ordered sequence of symbols. Basically, X and Y are ordered sequence of symbols. What we would like to do is find the length of the common subsequence of X and Y, right? And measure which gives one measure of how similar the two sequences are. So from X and Y, we want to find a subset that's most similar between X and Y, so that we can tell how similar X and Y are. One example of like such a case is something known as multiple sequence alignment. So say, for example, you have a DNA sequence of one animal or one species, and then we have a DNA sequence of species two, and then what we want to do is find out whether the two species or two creatures we have found, organisms we have found, are similar or not, or to what degree they are similar. So we will need something like the longest common subsequence problem solution to be able to do that. What would we do if we didn't have an algorithm for the same? You'd have to come up with your your knowledge of programming, and then come up with your own naive ways of calculating the longest common subsequence, right? Another example problem is, say, for example, an assembler. It could be a person or a machine receives parts of a machine to complete a mechanical design, right? So you're designing a product, and it depends on various parts that people need to feed in, or like we need to feed in to make this final product, right? Um, so and you as a designer know what parts you need and which parts depend on which. So these parts may have dependencies. For example, these two parts may be needed to complete this, and then all of these three may be needed to complete the fourth, and then the fourth will go in to a big piece as the product, right? um, so for solving problems like these, we need algorithms, because algorithms can be used to order these parts in a way such that you can tell, well, give me this part first, and then this one, and then this one, and then that will create a natural order in which you can, I can put things together or assemble them to create the final product. Once again, what would you do if you did not have an algorithm? What you would do is try it over and over again, and once again create a database of your solution, right? And then every time there's a change in your parts, maybe you add some parts or you remove some parts, you would have to do the trial and error again to create a new database where the old database does not work and you have a new one, right? So whereas having an algorithm enables you to automatically every time generate this order of parts, so that you can build the product without having to do a lot of hit and trial. One example, a small funny problem is, say, for example, you're preparing to go to a party or somewhere else, and then you need to put all of these things on before you leave, right? So you can only wear jacket after you have put on a tie, belt, shirt, and everything. So watch you can wear anytime. You have to put on your socks before you wear your shoes. You have to wear your undershorts before you wear your shoes, and so on. So say, for example, this is the dependencies that we have. Now what we want is to know which are the things that I can wear first and which are the things I can wear last, right? Now what I want is, so I see this graph. This graph can be bigger, right? It can be much bigger as well. What I want is an order of these activities, numbered 1, 2, 3, so on, so that I can simply follow the order and guarantee that I will not mix things up. That is, I will not run into a problem where I need to go back and start over, right? So such an ordering is called topological ordering. Topological ordering. And there are algorithms that take such a dependency graph and give you such an order where just by looking at the order, you can simply follow the steps in the order, or follow that order, like, guaranteeing that you'll never have to go back and undo what you have already been doing. Now, many of these algorithms have two common characteristics. One common characteristics is that there may be that the solutions may have multiple candidates, but most of them are not the best. In other words, um, finding the best is the challenging. So you may have problem P1, and then it may not be very difficult for you to come up with solutions. Let's say solution 1, solution 2, solution 3, solution 4. So finding a solution is not difficult, it's easy. The tricky part is finding the best solution. So that's what algorithms are sometimes designed to handle. So this is one common characteristics of algorithms, where we not necessarily worry about finding a solution, but we worry about finding the best solution, right, or the optimal solution. Another characteristic that's common to these algorithms is that they have a lot of practical applications, right? For example, the shortest paths algorithms obviously have the application of finding shortest path between two cities when you are traveling, right? We just saw an application of topological sorting, right? Similarly, finding shortest common sequence also has practical applications. So these algorithms have a lot of practical applications. That's one characteristic. And the second characteristic that we just saw is that the challenge is not just to find a solution, but to find a best possible solution, or an optimal solution. Now, there are some problems that are very difficult, also known as hard problems. One example of such a difficult problem is something known as TSP. Many of you may already be familiar with the problem, also known as the traveling salesman problem. Here's an example of a traveling salesman problem. Consider that FedEx has a central depot. So FedEx has a central depot, maybe somewhere in St. Louis, right? Each day, the delivery truck loads at the depot, right? So here's your depot, loads at the depot and sends it around to deliver mail to several addresses. So this has to go to various addresses, and then obviously at the end of the day, the truck has to return back to the depot. What FedEx wants to do is select an order of delivery stops that yields the lowest overall distance traveled by the truck. So you don't want to send your truck all the way to the end first and then come back to deliver somewhere that's very close, and then go back down to the further away place, and so on. So um, the problem here, the challenge here is to find out a path from your depot all the way back to the FedEx depot, such that you cover all the places that you want to go by shortest, like, by having to travel as less as possible. Um, Unfortunately, there is no known efficient algorithm for this problem. What this means is we don't have an algorithm that can give us a solution very quickly. Problems like these are also known as NP-complete problems, and what they need is approximation algorithms. That is, there is no algorithm that can always guarantee you to give you the best solution. So some algorithms may give you almost close to the best solution, and so on. So TSP is pretty much solved when the number of cities that you want to visit is smaller, say 5 or 8 or so on. But as the number of these cities in between increases, then traveling salesman problem becomes extremely difficult. And then what we have to look for is alternatives to solve these problems, where they have, like, sort of practical value, where we can have answers to solve to our problems in real world. Now, before we jump into algorithms, I also wanted to talk about cover some preliminary definitions related to algorithm. Um, what does an algorithm mean? An algorithm is nothing but a well-defined computational procedure that takes some input or a set of input values and then produces a value or set of values as the output. So basically, it's like a cooking recipe. where you have your ingredients, right? And then you have your recipe that finally gives you the food that's ready to be eaten. Now, we also want to understand what we mean by correct algorithm. An algorithm is said to be correct if for every input instance, it holds with the correct output. So if for some cases, your algorithm doesn't work, and it only works for maybe half of the cases, then we say that the algorithm is not correct, right? So for an algorithm to be correct, we assume that the algorithm, or we like, we need a guarantee that the algorithm always gives us the correct output given the same input. Now, data structure, as probably all of you already know, is a way to store and organize data in order to facilitate access and modifications, right? Now, you may be thinking why, we need data structures, right? So many of you may already know this, but the reason why we need data structure is because there is no single best data structure, right? Imagine two-man and truck loading a set of boxes in the truck, right? Is there a universal way to stack the boxes? Universal way of stacking the boxes? No. Why? Because it depends what we have in these boxes, right? If we have fragile things, we may not want to stack one on top of other. If unloading is a concern, that is, if we have to unload everything as quickly as possible, we may follow a different ordering, right? If we want to store a lot of things, then store more items or more boxes, there may be a different approach. So depending upon the algorithm that's being used and the need for the data, how frequently we want to access it, whether the focus is on reading or writing, we need different kinds of data structures. In this course, we will not focus a lot on data structures. Our focus will be on algorithms. Now, the next definition that I wanted to cover is the definition of analyzing an algorithm. So when we say we are analyzing an algorithm, what's very important to know is that we are not talking about whether the algorithm works or not. That's not analysis of algorithm. That's checking whether the algorithm is correct or not. Now, analyzing the algorithm already assumes that the algorithm is correct, right? But on top of that, what we want to do is predict the resources that the algorithm requires. For example, how much memory it needs, how much computational time it needs, how much network bandwidth it needs, and so on. So when we say analyzing an algorithm, we are already assuming that the algorithm works, and it gives us the correct answer. We are more interested in how fast does it run, or how much memory does it occupy, and things like that. Now, algorithms is a technology, and many of you might know that technology is for building products, right? Um, Products. So what the purpose of learning algorithms is thinking of this as a technology is so that we can use it to solve problems in real world and design new products. So when analyzing an algorithm, there may be many things to look at. For example, a computer program may need to have a lot of features. User friendliness, that is, how user friendly is your program or your algorithm finally, is an important concern. How robust is the program? How maintainable is your algorithm, right? How much time does it need to code it? How much memory does it occupy, how much network bandwidth does it use, and so on. So these are various parameters that we can consider when we are analyzing algorithms. But most of the time, we are concerned with the speed or running time of the algorithm, particular in this time where we have big data and we have a lot of data to deal with. Speed becomes a really big concern. And what is the best way to analyze running time? Obviously, the best way is to supply a huge input. Does your program still run if I have 10 to the power 9 input rows, right? And so on. Unfortunately, we cannot always test programs by supplying a huge input because it'll take a lot of time to test various algorithms if we every time supply an input that's really big. So we resort to something known as asymptotic analysis. And this is the tool that we will use to analyze the running time of an algorithm. What asymptotic analysis basically means is if I have number of items n, or if the um, the data input that I have is decided, the size is decided by n, and if in my y-axis I have running time t, then as I scale n, how does the running time increase? Does it increase linearly, right? So if I increase n, does it constantly increase? Does it increase exponentially, right? So the more inputs I have, the worse the running time is, right? Does it is it opposite exponential? That is, as I increase n, it continues to get worse, but after some time, it's a constant running time. So such an analysis is asymptotic analysis, and that's what we would like to study and focus here. Now, there are many algorithm design techniques. So even for solving the same problem, let's say P1, we may be able to come up with solution S1, solution S2, S3, and so on. Now, overall, algorithms can be designed with various techniques. One technique is incremental. We'll look at an example of an incremental technique. Another technique is divide and conquer. Another is dynamic programming. There are greedy approaches. There are genetic algorithms, and so on. So these are algorithm design techniques. Some problems are ideal fit for some design techniques. For example, problem P1 may be an ideal fit for incremental technique. The same problem P1 may be solved equally well by divide and conquer, right? But there may be another problem P2 that may be solved best by dynamic programming, right? Or there may be another problem P3 which may be best solved by greedy approach or genetic programming. So at the time of designing algorithms, we have these choices to try out various design techniques, and then once we guarantee that our approaches all are working, we can then move to doing the asymptotic analysis, right? That is finding out which runs faster and so on. So before we get into the asymptotic analysis, or before I discuss the idea of asymptotic analysis, I would like to review two sorting algorithms. One is the insertion sort algorithm, and the other is merge sort algorithm. And then with these algorithms as examples, we will discuss what asymptotic analysis are, and how we can use the techniques in asymptotic analysis to sort of assess or evaluate the running times of algorithms.